Okay. Let's hope it works. Okay. Hopefully we can start. Okay. Can you see the presentation at home? Yes, no?
Yes,
okay.
yes.
Okay, thank you. Okay. This was I think the last picture we saw on Friday. Yeah. So this was an example, as I told you, of a single transistor series pass regulator, basically a series pass regulator, where we are using a single transistor to, let's say, reproduce the output voltage of a Zener diode to the output. Actually, there is a small difference between the voltage on the Zener diode and on the output that is given by the dB, the base to emitter voltage of the transistor. We are considering large signals, so this means that we must consider the voltage to base, voltage base to emitter, voltage of the transistor that is directly biased. Someone of you also, if I don't remember, said that if we want better performances, for instance, here we see that the output resistance is a function of the beta, of the current gain of the transistor. We could use a transistor with an improved beta, that is a Darlington transistor. Okay, we'll see the Darlington transistor later on. Basically, if we have a Darlington transistor here, that means a cascade of two transistors, we will have a total difference between the Zener diode and the output voltage of 1.4. Because in the Darlington configuration, we have two base to emitter junction. Okay, so this is something that we must consider. Okay, the problem with the circuit here was that basically we have no feedback. So if there is a change in the output voltage, the system does not realize that there is this change, and so it cannot correct the output voltage. It's an open loop system. It works fine, but we need something better. That's why we moved to the next circuit. That is the two transistor closed loop, in this case, series pass regulator. I want to tell you that actually the real circuits are a bit more complicated than this one. But this is very interesting because it's relatively easy to characterize and contains all the key points of a more complicated circuit. So first we study this circuit here, this basic circuit, and then we try to improve it, adding more parts. Okay? I give you just a few seconds. I know that we already, I'll give you the slides later on, but probably if you take notes, even if you're at home, that might be interesting because not everything that I say is written on the notes. So or you may leave for later drawing the schematic diagrams, or if you draw the schematic diagram, you will learn how the different components are connected. So it can be a good exercise also for you. Okay. So I'm giving just a few seconds for those of you who are copying the schematic. Yeah. Okay. We are more or less done. Now I can start the description of the circuit. Finito? All right? Okay. So, what is this part on the left? This is something that we already saw. This is the equivalent circuit of what we have really on the left. As we saw in the past, we want to use a regulator basically for using the mains power supply and adapt it to the load that we want to energize, let's say. So all this part on the left, VDC, VR, and R filament, basically is the equivalent model of what? Of the transformer, input transformer, the rectifier, can be single, double, Weber, or Gretz bridge, the filter, basically a capacitor, and also, so we end up, with those three elements. The VDC, which is the average output voltage of the rectifier, or the rectifier and the filter. The VR represents the ripple that is remaining in the output voltage of the rectifier and filter. And then there is this series resistance which keeps into account the filament of the transformer, but also the resistive part of the diode behavior. So the diode behave like a sort of threshold plus resistance. And so this R filament is keeps into account also the resistor, the diode resistance. Sorry, just a local question. Se non vi dispiace posso chiudere un po' quella cosa perché effettivamente chiudere, grazie. Magari rimane aperto però un po' di freschetto. Un po' sudato. Ok. Okay, so now what? Let's have a look to the remaining of the circuit. If you just focus on Q1, transistor Q1 and R3 and the Zener diode, it is very similar to what we saw before. I go back to the previous circuit. You see here the series pass transistor, the resistance for biasing the diode, and the Zener diode itself. So this part of the schematic is there. We just have added something more. So Zener diode, this is the biasing resistance with some approximation, and Q1 is the series pass transistor. What we have added here is this part here. For instance, we have added 2 or 3 resistances. In this case, we added 2 fixed resistors and 1 potentiometer. We may have done it just with 2 resistances, R1 and R2. In this case, I added the potentiometer for something that I'm going to show you. But in any case, you can consider that the top resistance plus a part of the potentiometer is R1. The bottom resistance plus a part of the potentiometer is R2. This creates basically a voltage divider, a potentiometer, a total potentiometer. So, in first approximation, we can say that the voltage on this node is given by this formula here, you see? Is the output voltage divided by the sum of the 2 resistance multiplied by R2. That's a typical formula of a voltage divider. Don't look at the left, sorry. The other component that we added to this schematic is a transistor that is placed between the base of Q1 and the top contact, the cathode of the Zener diode. In the past, we had just a short circuit here. Now we have this transistor. The reason for this transistor is that it is basically what we call the error amplifier. The system checks the voltage on the Zener diode, compares it with what it gets from the output through this partitioner, and sends this voltage on the base. The transistor makes the difference between the 2 voltages, and if there is any error, it will control the transistor Q1. How? Basically, this transistor Q2 can absorb a part of the current that usually would go to the base of Q1, and also on the Zener diode, let's say. So depending on which is the situation, if the output voltage is too high or too low, Hello? Can you see me?
Now, yes.
Yes, okay, now we had the problem, the network is down here, so I'm using my tethering for connecting to the internet, okay. So if we disappear, don't be afraid, okay? We just don't have a network. In this case, I will switch off my camera, so I save some data, okay? Don't worry. My face is not very important in this presentation. Okay, now let's start again. And pure interrotta per sì. Un secondo. No, è avviata, me l'ha ancora avviata. The sharing. Okay. Now from home, can you see the presentation again?
Yes.
Okay, great. I hope that the lecture is going to be recorded, but it seems that it's still recording. Okay. So, okay, what I was saying, I don't remember, basically was that, so the transistor Q2, depending on what is the input, will modulate, will change the current that it absorbs through the collector, so that we can change the behavior of transistor Q1. If, for instance, the output voltage is going down for some reason, is reducing, the transistor will allow more current on transistor Q1 in order to increase the output voltage. Okay, so basically this is a feedback system. The output is controlled, and this error amplifier Q2 is going to modulate to change the behavior of transistor Q1. Okay, I almost described every component except for this one that I left as the last one. What is this R? Because in the past we took all the current for the Zener diode from resistance R3. You remember? So through resistance R3 we derived all the current for the Zener diode. But we have already discovered that for improving the behavior of the system, even with a simple transistor, if you want to block, let's say, the variation of the input voltage due to the ripple and stop them from going to the output, we discovered that we must increase the R resistance, the resistance for biasing the Zener diode. And so basically this is going to work also in this case. We will demonstrate that this is very important. For that reason, R3 may become so high that it doesn't give enough current for the Zener diode. But most of the current for the Zener diode is just for biasing the diode. So it doesn't take part to the variation of the transistor Q1. So in this circuit, most of the current for biasing the Zener diode is taken through this resistance RD here. Why from here? Also for another reason, if the system is going to work correctly, the output voltage will have very small variations. So this voltage here, VO, is very stable. The Zener diode, for working fine, needs a very stable current. So what is better than deriving its current from a very stable output voltage? We could have placed the RD on the other side, but if you put RD on the left of a transistor Q1, we have ripple here. While on the right, we don't have almost any ripple. The ripple is very, very small. So let's say the Zener diode needs 20 milliamps. Probably we will take 15 milliamps from here and only 5 milliamps from here. These 5 milliamps are needed for biasing also the transistor Q2 and are those parts of the current which can be changed by transistor Q2 and sent to Q1 or not, depending on the needs from the load, okay? So most of the biasing current for VZ is taken from RD. Now I go back to the whole circuit. And I want to show you that using this particular situation of the voltage partitioner for deriving the output voltage, the output voltage can be chosen according to this ratio here. That is very useful, because if you, for instance, consider that here I placed a variable resistor, a potentiometer, I can actually change the output voltage according to what I need. If one day we'll move to the lab here, to the experimental lab, you'll see that there are some power supplies which can give you voltages between 5 and 15 volts. So from 5 to 15 volts. And there is a knob that you can rotate, and depending on the position, you'll change the output voltage. That's the basically reason for having this variable potentiometer here, okay? But now we must understand which is the relationship between the variable resistor and the output voltage. How can we do that? Well, we simply look at the potentiometer here, at the variable voltage partitioner. We suppose once more that the transistor Q2 has no base current, so that we can calculate the output voltage of the potentiometer as it is connected to nothing. It's an open circuit on this point. So look at this relationship. On the right part, we see that the voltage on this node on the base of Q2 is equal to V output times R2 over R1 plus R2. And that's the typical partitioner formula. But if you look at on the left, we see on the left that actually the same voltage is equal to VB2 plus the Zener diode voltage. That's what we wrote here. So VB2 plus VZ. Well, if the system works fine, this relationship must be kept true. This means that this is a balanced situation for the closed loop system, and we can explicitly okay, are you still there?
Yes.
Are you there from home?
Yes, sir.
Okay. Yeah, okay, I cannot, because again we saw a voltage variation in the light here. So. Okay. Okay. We can keep on. So, if you see here, what I did was basically to resolve the whole equation in terms of VO. Basically, I take this ratio here and multiply the left-hand side by times this inverted ratio. And so I get R1 plus R2 over 2 VB2 plus VZ. Or, if you prefer, we can write it as VB2 plus VZ, to simplify, 1 plus R1 over R2. That's the final relationship for the output voltage. So the output voltage is given by a fixed quantity, that is VB2 plus VZ, times this term here that depends on the ratio between the two resistances. If I increase the value of R1 and I reduce R2, the output voltage can increase. Obviously, there is a minimum. If I connect directly the wire of the basal transistor to the output voltage, this means that R1 becomes 0. So the minimum output voltage is VB2 plus VZ. The maximum can be infinite. Obviously, infinite does not exist, but can be very high. Then we'll see also at the end of this discussion that having a ratio R1 or over R2 too high is not good, because the output performances of the system will go down. There is a problem, and we'll see that. So basically, we see from this formula that the output voltage is VB2 plus VZ. Now, I may wonder, okay, this is good, it seems to be working, but what happens if I increase the temperature of the circuit. One of the things that we must study is how the system behaves in terms of temperature variation. From the output voltage, I see that the output voltage depends on VB2 plus VZ. We know that the VB2 will decrease by 2.2 millivolts per Celsius degree. If I find the Zener diode that increases by 2.2 millivolts per Celsius degree, I'm fine. This means that we must use Zener diode around 6.2 volts, as we saw before. Okay. This is nice, but at the same time it tells us that the minimum output voltage for this voltage regulator is around 7 volts again. We cannot stabilize voltages below 7 volts if we use this simple circuit here. But we already studied that we can make, for instance, what? The band-gap reference systems, circuits. So instead of using a Zener diode of 6.2 volts, I may be able to build a band-gap reference voltage system circuit, which has a much lower voltage, output voltage, but temperature noise. There's no way to lessen. Okay, so in the past we studied, for instance, that we could make band-gap references which were intrinsically balanced in terms of voltage variation. For this situation, instead, here, we instead would like to have a band-gap reference with a positive voltage variation. We can design, we are free to design with this voltage band-gap regulator with these performances. So we can try to reduce the output voltage of the Zener diode and using a band-gap reference circuit. I hope, yeah, I said most of the things that are, yeah, okay. Your colleague was asking here, why do we have 7 volts at the output? Because we have VB2, which is 0.7, plus VZ that for thermal compensation is 6.2. So if you use a Zener diode, we get 6.9. Okay. So no lower voltages unless we change the Zener diode and we use a band-gap reference, basically, which is thermally compensated. Okay. Ad aspettare. Sentiamo urla. Andiamo a recuperare Martorana. Quelli erano armati di trapano percussione. Okay. Now I'm waiting for one colleague of yours that tried to stop the noise. Dov'è? Sono preoccupato. Non vuol dire. Okay. Maybe I'll move to the next slide. Aspettiamo qualche secondo. Okay, so once we have seen more or less what the circuit is, again we want to calculate, to define the main parameters for the circuit. So what we are going to do now is to try to calculate the important parameter related to the performances of our circuit. This is something that we have already seen. Sorry. Sorry, can I stop just one moment, please? Okay, once. Devo fare altri 3 pirtusi, ma non è essere quello. Cioè, saperlo se sta a casa che non c'è sta cosa. Sorry again, but I'm here. No, just they are changing some windows just on the room below us. So it's, I don't know if you can hear the noise. It's very hard to do any less. Anyway, let's go on. Sorry, I ran to the stairs. So, I'll try to speak louder. What I was saying here, quindi questo è il buco numero 1. Adesso vediamo anche. So, what I was saying here that if we remember what we said about the typical expression of the output voltage can depend on many parameters that are the input voltage, the load current, and the junction temperature, the ambient temperature, basically. In a more formal way, we can explicitate the dependence or the variation of the output voltage depending on those variables. And so I wrote what we usually call a differential, let's say, where the output voltage variation can be related to the partial derivatives of the output voltage in terms of the 3 variables times the variation of the single variable. Okay? We already saw something of this for the diode, for instance. And also we saw that we called those 3 terms, so the partial derivatives, as stability factor or stability coefficients. The stability factor of the voltage due to the input voltage, to the output current, IL, or to the junction temperature. So those were the stability factors. Here I want to show you that sometimes, instead of these stability factors, you will find some other coefficients that are called sensitivity, which are very similar. What is the difference? If, for instance, we consider the stability factor of the input voltage, that is the variation of the output voltage in terms of variation of the input voltage. So the derivative of V out in terms of V in. Instead of just defining this, if we consider a sort of percentage variation of each terms, we write the variation that the output of the voltage divided by the voltage itself. So this is a sort of percentage. If you want a real percentage, you have just to multiply times 100. So if you here you write per 100, you get the percentage. But this 100 is going to be cancelled up and down, divided by the, say, percentage variation of the input voltage. Okay. If we explicitate this formula, we can write it as dVo and dV in that represents our old stability factor times V in over V out. So that sometimes we'll find in the books this sensitivity SVO, SV over V in. Some other times we'll find the stability factor. So that's why I'm defining them here, just in case you find them in some book, you know what they're talking about. We will work simply with the stability factor, a bit easier, so we do less calculation. Okay, this was just a sort of parenthesis to remember what we are considering now. What I'm going to do now, instead, is the dynamic study of the circuit in order to calculate the 3 parameters I already told you. Well, in order to make things easier and to reduce the number of calculations, here making another hole, so you know, let's hope, wait until they stop. No, ma tanto si propaga dal muro. Si propaga il rumore, dice, è il rumore. Vuole chiudere per sentire. No, tanto si propaga, dico, dal muro, dal pilastro, perché stanno facendo le sono esattamente qua sotto, quindi non c'è speranza. Come? Sì. No, ma la prossima volta se l'avessi saputo, ce ne stavamo a casa, almeno era tutto più facile. Ci siamo abituati male in questi 2 anni. Allora, sorry, so I was saying, okay, just to save some calculation, we must say that for what it regards the junction temperature variation, we already said something. Basically, we must choose a diode that compensates the transistor temperature variation. So I will skip the part related to the temperature variation because more or less we know how to face this problem. Okay. I can also say something. This is a typical question for the exam. What about the thermal variation of transistor Q1? Because in this formula we just compensate the VB voltage of transistor Q2. We don't say anything about Q1, but what is the point? Due to the fact that the transistor Q1 is in the feedback loop, the system will automatically compensate any variation of the VB of Q1. So we don't care about Q1 simply because the system is a feedback system with a negative feedback and will automatically compensate any problem that is in this feedback loop. Okay. So we can skip the part related to the temperature variations. Non la vedo convinta. No.
Allora, io ho visto che ho l'anello di retrazione, non ho problemi con la temperatura, la temperatura con
Okay. I was answering your colleague because she's not convinced about the VB variation. We have a situation, so we consider a determinate situation. What happens if the VB of Q1, for instance, reduces? If the VB of Q1 reduces, there will be probably an increase in the output voltage. But the feedback system will try to keep the output voltage constant. So the transistor Q2 will compensate everything in order to keep the output voltage constant. We don't care if the VB increases or decreases. We just keep constant the output voltage. Okay. Okay. So we can say that we already know how to bring this coefficient here, or STJ, to 0, more or less. At least in a first approximation. We don't go further than a first approximation. While I want to see how the output voltage depends on the input voltage. Again, this is basically how can I predict how much ripple I will have in the output voltage for a given ripple in the input voltage. I would like to have no ripple in the output, even if I have some ripple in the input voltage. That is the reason, basically, why we are using this electronic stabilizer for the input voltage. Okay. In the past, without electronics, we just would just say, if I want to reduce the ripple, I increase the capacitor in the filter. But due to the fact that for the amount of ripple that we want, we should use an enormous capacitor, we tried to do something different. We still have some ripple at the input voltage. We want to just eliminate the ripple at the output. How can we do that with electronics? And that's the reason why we must calculate the stability factor related to the input voltage. Okay. How can we do that? Okay, first of all, we must do a number of considerations, a number of flashes, standards. Okay, so here is a list of considerations, starting consideration, let's say. First of all, given to the fact that we want to calculate the variation of the output voltage due to the input voltage variations, we must consider other parameter constants. So, for instance, we are considering a fixed IL, a constant IL, and also a fixed temperature, because we must study one coefficient at a time. Okay? So I must suppose that if I see what happens to the output voltage when the input voltage is changing, the IL and the temperature must be kept constant. If IL is kept constant, basically I can suppose that this IL is the same as the current in the filament resistance here. So if I take the product IL times R filament, this product is constant. So the voltage drop across the filament is constant. This means that if the V input has a variation, the same variation will be also in the node A. Prego. In pratica, okay. So your colleague was saying, how can we suppose that IL is constant if there is a variation, also a part of current is going down? Basically, because in a real circuit, if you want to do some tests, we can change the R load with the current generator, absorbing a fixed current. Or in this case, we can say, given that the system is very stable, I can suppose that the VO is constant, and so the current absorbed by the load is constant. That's first approximation. If I want to be more precise, I put a real current generator there. Okay. So this consideration was useful for saying that given that the voltage drop across our filament is constant, the same ripple that we have here at Vin is at the node A. So we have, it's like if there was no R filament, basically. The ripple, VR, is over node A. And that's a first point. The second consideration was that if we are working with a constant current and also the system is working fine, I can suppose that the output voltage, VO, is quite stable. VO stable IL constant. IL constant means also the base current of Q1 constant, because the base current of transistor Q1 is the IL divided by the beta, the current gain of transistor Q1. And if the base current is constant, also the VB of Q1 is constant. So what is the voltage on the node B, on the base of transistor Q1? VO, that is constant, plus VB1, that is. Let me see. There was a voltage drop again. I don't know if you are still connected or not. Are you still there? Okay, great. No, because here everything is going down, voltage network. Okay. Unfortunately, we are working with.
Here too.
Okay.
But,
okay. No. Okay. Great. So the batteries are powerful. So as far as the batteries will last, we are safe. Okay. Okay. So why am I focusing on the point on what I said? So basically, we saw that the node B. Oddio. Collegatevi con Teams, sorry. Here also the projector went down. This is one day that we say I should remain in the bed today. Okay, no. Awesome. Sorry, moto. Okay, so now we are just waiting for the projector to start again. Sorry. One second. Guardate, mi metto una mascherina. Mi metto per correttezza. Tanto non cambia niente. Allora lei dice proviamo a fare questo. Questo o questo, perché è scemo questo computer e questo computer. Ah no, questo è switchato. Posso vedere la cosa, no, non toccare molto, perché non è che è andato in protezione, posso fare una cosa, lo spendo un secondo. Sorry. Ok, positivo. C'è quel brutto LED azzurro che lampeggia.
Forse ora si sta accendendo.
Ah sì, no, quello.
Io non la schiena posso accendere adesso
Ok, la lampada si sta accendendo. Ci sono 3 spie azzurre, che abbondanza, giusto? No, 3 o 2, sì, 3. Brutta cosa. Posso provare? Allora, lui lo sente. Ok, so we are on again. Okay. Are you still connected? I hope so. Okay, let me see if I... Okay. Yeah, it says we are connected. Okay, great. Okay, so we are considering what? Also, my brain has been resetted. Okay. So what we are saying is that the node B has a fixed voltage, okay, because given by VO, the fixed plus VB. Node A has a voltage ripple on it. So, considering a fixed voltage B, it's like considering dynamically that B is grounded, while we have a ripple voltage on node A. This means that the whole ripple voltage is across the resistance R3. So we have this ripple voltage connected, let's say, between A and B. Now, if we have this ripple voltage across a resistance, we will have a ripple current through the resistor R3. Okay. This current is going like this way from left to the right. I can try to plot it. So we can suppose that we have a ripple current that we call IR3. Maybe I already wrote it, IR3. That is given by this ripple voltage across the resistance R3. What is the effect of this current? In the previous circuits, this current IR3, when we did not have Q2, the current IR3 went all through the base of Q1, and this generated a current and a voltage variation through transistor Q1. So we had the ripple in the output. Okay, so if we leave there the current IR3 and it goes, sarà 500 metri più o meno, si sarà fatto fuori qualche antenna televisiva. So if I was saying, if I leave the current there, impavido, sorry, I have to check something. Okay. Okay. Now, just to have an idea of how much the storm is going to last. Okay. 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 La situazione si dice, okay, I'll show you this, I don't know if you know this website. I show this website here. Okay. That shows in real time the position of the thunderstorms. So actually, listen. To do lesson. You see what is going on? It's a perfect thunderstorm, as I say. Okay. Okay, great. Let's try to keep doing the class, the lesson. Sorry. Okay, Mama. Okay. Okay, so what I was talking you about this current IR3. The current IR3, okay, as is written here, can be calculated as VR over R3. If we don't have the transistor Q2, all that current goes to the base of Q1 and will alter the output voltage VO, given ripple in the output. Well, what is the effect instead of transistor Q2? Transistor Q2 should be able to drain this current IR3, that is a sinusoidal current basically, or trapezoidal current, in order to keep the current through transistor, the base of transistor Q1, as constant as possible. In this way, the system will give a flat voltage in the output. How can the transistor Q2 do this? Well, we have to discover something. Basically, if we want that the current through the collector of transistor Q2 changes, there must be a change in its base to emitter voltage, at least in the dynamic part of VB. If we suppose that the Zener diode is perfectly flat, cioè perfectly constant in terms of voltage, we must suppose that this signal of the variable signal that changes the current in the collector Q2 must come from the output. This basically means that we must tolerate a minimum ripple in the output, because the minimum ripple in the output is the signal that, subtracted to the Zener voltage, will change the conductivity of transistor Q2. So definitely we must tolerate a certain amount of ripple in the output, otherwise the feedback system does not work. That's typical for the feedback system. We must tolerate a variation in the output. We can reduce to almost zero the variation only if we increase to almost infinite the gain loop, the loop gain. Okay, so if the gain of the feedback loop is going to infinite, we can have an almost zero variation in the output. We must do some calculation in order to understand how much ripple is left in the output, depending on the situation that we have in front of us. Just before we go on, we said, we talked about variation and fixed values. Just to remind you that usually when you study a circuit, we indicate with capital letters the static values. Like, for instance, I should have a static current through the resistor IR3, the resistor R3 that we call IR3, which is given by the static voltage between A and B divided by resistor R3, plus a variable amount of current that can be calculated as the ripple voltage divided by resistor R3. The static component in our discussion will not change. We will only see the variation, the dynamic components of the current IR3. Okay. What we said about the transistor is already written in this part of our presentation. If you want, I know that there have been a lot of interruption. Can we stop 5 minutes, hoping that the situation will improve a bit? Okay, and we keep the lesson in 5 minutes, okay? Let's stop for 5 minutes now. Okay. So this part is a bit delicate, so we must be 100% concentrated on it. Okay, so we are more or less at this point here in the slide. What I'm going to study now with you is how to phase the study of this coefficient, stability coefficient here. For doing that, we must certainly remember something about the feedback theory. Before doing that, we must understand what kind of feedback we have in front of us. Well, I can tell you that this is the first consideration about our feedback system, but it's not really what we are going to use for one reason. This is the schematic that summarizes what is going on in this circuit. Basically, we have an output voltage. We take a part of this output voltage through the beta network. By the way, be careful. When I talk about beta here, I mean the block beta. You must not make confusion with the beta that is the current gain in a single transistor, okay? Be careful about that. Unfortunately, they use the same letter, but from time to time we'll understand which beta is the one that we have in front of us. Okay, so I take the output voltage, I reduce it using this voltage divider here, and I send it to a summing to another, which actually takes the difference between a reference voltage, Vz, that is the voltage coming from the diode, and this feedback voltage. The difference is sent to the amplifier, to the main amplifier A. Let's see what we are talking about in the original circuit. Well, the Vz is basically the voltage on the Zener diode. The feedback voltage is the voltage which goes back to the base of a Q2. The transistor Q2 takes the difference between the emitter and base voltage, which we may consider it as an error signal. And depending on this voltage, VB2, it will manipulate the amplifier, that is basically given by the output of a Q2 and Q1, in order to keep the output voltage constant. So that's the feedback system. If you want to understand what kind of feedback we are talking about, well, the output voltage is sent also to the beta feedback block. So this means that we have a voltage feedback or parallel feedback, as we called it in the past. Then we take the output of the voltage partitioner here, and we subtract it to the voltage from the Zener diode. So just because we are taking the difference between two voltages, it must be a series feedback or voltage feedback. Okay, so basically this is what we call a series parallel feedback system. But is this actually what we are interested in now? Well, in this point, we are not interested in understanding the dependence of output voltage on the Zener diode voltage, because we said that more or less the Zener diode and the transistor are stable. Temperature, we compensated the temperature variation. While we are more interested in understanding what is the dependence on the output voltage on the ripple voltage. We were also able to transform this ripple voltage in a ripple current. But if we look at this picture here, we cannot see either the ripple voltage or the ripple current. So this schematic diagram must be changed a bit. It's not the right one for doing our consideration. Next slide may be a bit confusing, but look only at certain part, okay? No, it's the other one. Okay? It is more confusing than this. Okay. So the point here is our schematic. I copied the same schematic. So what we are interested in is to see where this IR3, that is the ripple current, is being injected in our amplifier. So what we do actually is to do a change in the previous schematic. The previous schematic was this one. In some way, we are injecting the ripple current here in the block A. So the best thing to do is to split the block A into two blocks, because the block A was the sum of Q2 and Q1. Now we separate the block A into two blocks, A1 and A2. If we do this consideration, well, this is the output voltage VO, that's the partition, voltage partition, okay. Then we have the sum of VZ and the voltage from the partition, that is the base emitter junction of of a transistor Q2. But then we have the current generator, that is the output of transistor Q2, that is basically this amplifier A2. We are injecting the current, the ripple current, between the collector and the base of transistor Q1, the collector of transistor Q2 and the base of transistor Q1. So we must add a block here, and in this case the feedback is a current feedback, because we are summing an input current IR3 to which we subtract the collector current of transistor Q2. The remaining, which is IR3 minus IC2, becomes the IB1 current, which enters the block A1. A1 is the transistor Q1. So if you see, we had to rearrange the blocks, add something, and in this case, with the schematic, what we have that actually we have a new beta block, which is made by the voltage partitioner and the transistor Q2, basically, and the Zener diode. For us, all that part is the new beta block. The signal, in our case, is the ripple, which is considered in terms of a current, ripple current here. Okay. Oh, I had a flash on the, oh, okay, it's still there. Okay, so now, what we are going to do is something quite strange. For us, the signal now is the ripple current. We want to see what is the variation on the output voltage. For our purposes, we would like to have no voltage variation when we have a ripple current here, or try to get the minimum voltage variation. So what we are going to do is to study the whole circuit and see under which conditions the voltage variation is very small. This means basically that we can define a gain in terms of VO over IR, and we want to bring that gain to 0. You can consider also that the kind of gain that we are going to consider, that is output voltage and input current, is a trans resistance. So we are not considering a pure voltage gain, but we are considering a gain that is a trans resistance. That is typical for those amplifiers whose output is a voltage and the input is a current. So those are trans impedance amplifiers, or trans resistance amplifiers. And I wrote here that actually we have a voltage feedback, so a parallel voltage feedback at the output, but a current feedback is again parallel at the input. So this kind of schematic is a parallel feedback system. This is something just for remind to those of you who remember what is written on the cell transmitter. Okay, so now this is our new control system that we must study. There is one block A, that is basically the transistor Q1, and there is one block that is made by voltage partitioner Q2 and the Zener diode. What we did in the past was to derive the appropriate parameters for this block here, change the block with the new model, with, in this case, were y parameters, parameter y, and then try to study the whole circuit. And that is what we are going to do now, if we have time. At least we'll start to do that. This should be the very confusing. Yes, this is a bit more confusing. Okay, we can admit that it is. But it's not so confusing if you just see what I did. What I did was I took the previous slide, this one, and I circled with a red box the parts which are the beta block. It's also a bit smaller because I did not have much room. So this is the same schematic as before, no change. What is the beta block? The beta block is the voltage partitioner, the Zener diode, and the transistor Q2. Everything here is the beta block, basically. We just neglected the RD. Doesn't do any effect in this situation here. So now I have to schematize in some way this red block, that is the beta block. How can I do that? I just copy and I consider the dynamic model of everything that is inside this red block. If you see, I can consider, for instance, the output voltage, or well, the output voltage variation as this voltage generator VO here. Okay, so this represents only the variation, not the static part. The static part is constant. Then we have, in some way, a variation in the output voltage. And so we have a voltage partition that is R1, R2. See, R1, R2. I take the signal and I send it to the base of the transistor Q2. This is the model, simplified model, of transistor Q2. The R pi, the base to emitter resistance, R pi 2, and the current generator, driven current generator, GM2, P pi 2. Okay, plus what? The Zener diode. The Zener diode is made by two equivalent components, a fixed voltage VBZ plus a resistance RZ, we can call it RZ. So in the dynamic model, we have only RZ left here. Okay, that's it. Now what we are going to do is basically to simplify this model in order to calculate what? We are considering a parallel schematic for the feedback system. So we need basically, this is the block, the equivalent model of the block beta. You see this part here. We need what? An input resistance, let's say, for the beta block. In this case, we can write it as an admittance. It doesn't change anything. It's like Y22. Then we need an input admittance for the, so an output admittance for the block, beta. And then we need a current generator controlled in terms of voltage. So it's a voltage-controlled current generator. Some of you last year had a simplified version of this block, but basically just call it R or O, something like that, RI, just different names, but basically it was the same thing. This YI2 parameter is also what usually we call beta parameter in the feedback system, okay? So just to increase the confusion. But anyway, so what we must do now is, starting from this block here, try to identify the parameters which are in the block here. So we must discover how much is the Y22 on this block, how much it is the Y11, and how much it is the YI12, so the controller generator. We move a bit further in order to simplify the schematic. We see this voltage VO, R1 and R2. What we want to do is the Thevenin equivalent of this part. So we simplify the system, because otherwise now we have 1, 2, and 3 voltage loops. It's a bit complicated. We can reduce on one loop the system if we just take the Thevenin equivalent of R1, R2, and VO, and that's it. We need an equivalent voltage that is VO times R2 divided by R1 plus R2 and a series resistance which is just the parallel of R1 and R2. Ok? Vi convince? Questo è Thevenin di questa cosa. No, si vede un po' perplesso. Okay. Unfortunately, I cannot see your faces at home, but I can only see the faces of the students which are here in the classroom. But if you have a problem, please stop me and tell us. Okay, now basically I will use both of them for deriving all the parameters. For instance, if I ask you how much is the y11, that is the y11 is the resistance admittance that we see when we short circuit the other side of the equivalent cell, equivalent box, quadrupole. So if we short the output here, we don't get any voltage, VO. Basically, the current generator will open, and so I will see this Y11. I'm going to do that also here. If I short circuit VO, there will be no voltage, no signal here. Probably the V pi 2 will be 0. And so, what is the current which goes into the system? This IC1, it's 0. Because this system is driven by the V pi 2 voltage. Things were different if we considered also the output resistance of the transistor. But for simplifying things, you basically can say that we have no input current. Having no input current means infinite resistance or zero admittance. The reverse is conductance, basically. So I can say that the Y11 parameter is basically 0, because the input resistance that I see from the collector of the transistor when I short the input is basically 0. The infinite, so the admittance is 0. Okay, so that was useful for this part. Then I want to know something about the Y22. Y22, or if you want R22, is the resistance that this voltage generator VO sees looking on the left, to the left. I can still use this schematic here. It's good enough. If I consider the resistance that he sees, basically the resistance seen by VO is VO divided by the input current of the system. But it's quite easy. Here we can just have a look at the system and find out how much is the resistance. Well, the resistance that I see here is basically R1 in series with the parallel of R2 and everything that I see looking into the base of a transistor. What I see looking into the base of transistor Q2 is, if you remember, R pi 2 plus Rz multiplied by 1 plus beta 2. Look at this formula. I have the R pi 2 plus 1 plus beta times Rz, okay, that is in parallel with R2, and here we are, plus R1. So basically that's the formula. The Y is an admittance as conductance, so I must take the reverse of it. And that's the input resistance of the circuit. Okay? Now we have the last point. I must determine how much is this Y12 or beta coefficient. Okay. How can I do that? I use this circuit on the right. One way of doing that is to consider only the input loop, voltage loop here, this one. And what I say is that the input voltage, that in this case is VO R2 divided by R1 plus R2, this term here, is equal to the sum of the contribution, the voltage drops across R1 parallel R2, R pi 2, and Rz. Okay. In this case, it's easier if we suppose an input base current IB2. This current goes through the R pi 2 resistance, and generates what we call V pi 2. Or we can also say that basically the current generator, driven current generator, gives a current which is beta 2 times IB2. They are basically saying gem 2 V pi 2 or saying beta 2 IB2 are exactly the same things. Okay, so I use this second formulation. Why? Because now I have to add, where is it? I have to add what? First, the voltage drop across R1 parallel R2. You see, I just put in evidence IB2, and first I multiply by R1 parallel R2, plus IB2 R pi 2, that is this one, plus RZ, but RZ is through RZ we have a current which is given by IB2 plus beta times IB2. So that's why I write IB2 1 plus beta 2. That's the total current through the resistance RZ times RZ itself. Okay. Now I remember that I can express IB2 as IC2 divided by beta 2. And I put it here. Okay. Why am I doing that? Because I want to know what is the ratio between the current through this generator here and the input voltage. And I have what? IC2 basically is the current through the transistor. So it is the current that goes from here. The Y11 is a 0. And also we have VO. So it's easier from this relationship here to do what? Okay. I already placed the IC2 over beta 2 instead of IB2. Now I have a denominator IC2 and I must divide it by VO. So I must take, yes, this one, Y12 is IC2 over VO. I simply bring VO here. I leave R2 over R1 plus R2 on the denominator. Then we had a beta 2 coming from the IB2, which was sitting here, and I bring here, and we get to this denominator here. And then the denominator is simply all this part here. Okay? So if we didn't do any mistake, we shouldn't have done any mistake, that's the final result. This is what we can call Y12 or beta, or in the books they call it G capital M. It's a sort of large GM, transconductance of the system. Why is it a transconductance? Because we drive the circuit with a voltage and the output is a current. So that's a big transconductance. From now on, we just use GM and we leave the formula here. Just at the end, we'll do some consideration about this GM. Okay. Now that we have calculated this GM, what time is it? Okay. What I can do is the following. I change the slide. And I just recopied once more the whole schematic here, but we know that what? That if you want to consider to study the system under the feedback theory, we must substitute the beta block with the equivalent model. And what is left for the beta block was basically the Y22. Y22 is the resistance that is seen at the output. So we have Y22 at the output is here, you see, that's the output voltage here, and we must put here the Y22, and that's what we did. All this part here will be substituted by the Y11 that is 0, so it's not there, plus the GM VO that was the Y21 GO. This part here, Y12, sorry. Am I wrong? Questo per caso è 2-1? Dovrebbe essere. Oh no, no, adesso no, 1, 2, okay, no, this is right, okay. Because the I1 is Y11, Y12, okay, no, that's right, okay. Sorry, okay, so I was saying we have to put here the equivalent current generator, GMVO. And we apply it on the base of a transistor Q1. So if you see this picture, Q1 is left there. Dynamically, I can say that Q1, if I neglect the filament resistance, that the voltage of Q1 in first approximation can be considered a constant. We know that there is some ripple, but for our purposes, does not change anything if we just put on the ground, dynamically, the collector of transistor Q1. The output is the meter Q1 that sees the load, our load, and also sees the equivalent impedance, admittance of this block here, of the input of beta, Y22. On the base of transistor Q1, no, dinamicamente no, adesso ne facciamo un'altra ancora. Oh, okay. I don't know if you're still there. Okay. Are you there from home?
Yes.
Oh, okay. Still alive. Okay, sorry. Okay. No, okay, just basically because this transistor Q1 behaves like a common collector, we know that we can take it to ground. It does not change much. No, it doesn't change much because most of the control will be given by the base. There is another consideration that I'm going to do. No, okay. So sorry, I placed here the equivalent output current generator, GMVO, that was the Y12, okay? Then we have the resistance R3, we have all this stuff here, but we said that basically it looks like we had a current generator which gave a current through resistance R3. So basically there was a ripple voltage here that was connected to the node A and resistance R3. Given that we must consider a current feedback, we can transform the ripple generator and the resistor R3 into a current ripple generator in parallel with the resistance R3. That's a Norton transformation. Sì, ma ho detto, siccome il transistor your colleague was saying, what about the collector of transistor Q1? It is connected to the same point. Due to the fact that the transistor Q1 is behaving like a common collector, basically the output does not depend on the collector voltage. We can simplify it basically, okay? So we can consider that it doesn't change much if we consider the collector at the ground. We are simplifying a lot, otherwise we lose our life on these simple circuits. It's not working. Okay. What we studied was also that when we wanted to study the feedback system, we studied which was the amplification of the system without the feedback generator, that we call the A amplification, and then we added the feedback dividing this amplification by 1 plus beta A. Okay. In particular, if I switch off this generator here, it will be an open circuit, okay? Because this is a current generator. So if I remove this generator here, it will be an open circuit. I can calculate the open loop gain. In this case, it's a resistance gain, it's a trans-resistance gain, because the gain is given by the ratio between the output voltage and the input current. So we remove this generator here, and we must calculate this AR, the ratio between the output and IR3. How can we do that? Well, the good news are that transistor Q1 is a common collector. So basically, the output voltage will be the same as the base voltage of this transistor. So we don't take care about the wire. We removed the current generator. We must simply calculate how much is the signal on the base of transistor Q1. The signal on the base of transistor Q1 is given by what? By the current IR3 that is closing over R3 and over the input impedance seen by the base of Q2 that are in parallel. So basically, this current will generate a voltage because it's flowing through the parallel of R3 and of the input resistance of transistor Q1. So first, we calculate the input resistance seen on the base of Q1 that, remembering the past formulas, was R pi 1 plus 1 plus beta 1 times Y22 in parallel with R load. And that's it. Okay. So that's the resistance seen on the base of Q1. But if I want to simplify, I can consider that actually this resistance here is high. Probably is much higher than resistance R3. Because this part here is multiplied by at least beta 1 times. So if we want to do a small simplification, I can neglect all that part here in comparison with R3. The two resistances are in parallel. I say that this is almost infinite. I just consider only R3. So the voltage on the base of Q1 is given by R3 times R3. The output voltage is equal to this voltage. If I want a ratio between the output and IR3, I get R3 only. Okay? So the out is the same as here. Here the voltage is IR3 times R3. I must divide by IR3 and I get only R3. So this R3 is the trans resistance gain of my circuit. Ok? Cosa non vado Come? Esatto. So the out is equal to the base. Okay, so that's it. Okay. So the open loop gain is R3. If we want the close of the loop gain, we turn on again this generator. When we do that, we must divide by 1 plus A beta, where A is this AR, beta is the GM that we found before, and so I can write that the trans resistance with feedback, again the output divided by IR3 when the feedback is there, so when we turn on again GM, VO, is equal to AR divided by 1 plus beta IR. That is not a bar, beta AR. Okay. With all those simplification, AR is R3. Then we have 1 plus GM over R3. If GM R3 is large enough, we can approximate with 1 over GM. Okay. And we are fine. So 1 over GM is more or less the trans resistance with feedback. But that's not all. We have just a last step to go on. What we wanted at the beginning was the output voltage variation due to the input ripple voltage. So we are not satisfied with the trans resistance. We want a voltage over voltage gain, a voltage gain. We simply convert this trans resistance gain in the voltage gain. How? We remember that this is IGM, 1 over GM is V out divided by IR3, but IR3 is VR over R3. So I simply take this and put it there. So the voltage gain with feedback is VO over VR. That is also the stability factor. And we can calculate it as VO over what? I got confused. over IR3, R3, that is the VR, yes. It can be written as the gain, resistance gain with feedback divided by R3, so we get 1 over GM R3. Okay, that's it. I hope it looks correct, but it should be correct, okay? No. VO over, no, that's VR over IR3. Questo è V-out. Quello era VR su R3.
VO su
Sì.
IR3 è AR, no AR.
Sì, aspetta. VO su IR3 è ARF. Perché sto mettendo qua.
Perché le sono stessi?
Chi? No. Poi la nuova situazione. Questa, io voglio sapere, dopo che ho chiuso il feedback, quanto è il rapporto tra V con O e IR3. Scusa, VR, scusa.
Dico AR, sono definiti come VO su IR3.
Uno in un caso senza generatore, l'altro caso con generatore. Il secondo, esatto, sì. Ok. Now we found that the feedback gain, the voltage gain with feedback is basically 1 over GM3 R3. Okay. Very nice. What can we do with that? Here I reported the final formula, the voltage feedback, so the voltage gain with feedback 1 over GM3 R3, and also the expression, the full expression of a GM, because that's useful for something. First, how can I reduce the voltage output variation due to the ripple? This is one of those cases where you want to give, to bring to zero this ratio. Because if we bring to zero the ratio between the output variation due to the input variation, it means that the output voltage is not sensitive to the input variation. The formula tells us that we can both increase GM or increase R3. It is something that we have already seen. If we substitute R3 with a current generator, probably we'll increase the dynamic value of this R3, and so we'll get a much more stable system. That is why I told you R3 must be high. It can be still a resistance, or can be a current generator. Usually, we want to have a current generator, maybe with not that much current. It's not enough of this current for powering the Zener diode, and so we derive the supply for the Zener diode from this resistance here. That's the other point. If we look at the GM, how can we change the GM? At least with this circuit, there is not much to do. We should increase the beta of the transistor Q2. That's one way. We can use the Darwin. But in this case, but it's not correct, because beta is here, but it's also here. So if you increase the beta, probably the ratio will not change that much, given that the beta is on top and the bottom. But this is another problem why I showing this formula here. Here we have the ratio of the partition voltage divider. If we increase R1, hopefully we will not drop downstairs. Okay, that's the point. If we increase this ratio too much because we want to have a very high voltage output, so we are increasing R1. If we increase R1, this term will decrease. And also will decrease more because R1 is also in the denominator. So in general, G con M will decrease. If G con M decreases, this number increases. So this means that if we increase too much the output voltage, also we decrease the performance of the circuit. The circuit becomes less stable. So there is more ripple in the output. So that's why usually we don't want to have a very high output voltage using the circuit, because otherwise the output ripple will increase. So in a circuit like this, when we change the output voltage, changing the potentiometer, we also increase the ripple in the output voltage. That's something which we can't do anything about it. That's a defect of the system. If we, in some way, we can say also this, if we increase this resistance here, we are decreasing the gain, the loop gain of the system. But a high loop gain was okay for reducing the ripple. If we decrease the loop gain, the ripple will increase. So when we decide the variation on the output voltage, we must consider that also the ripple will increase in the circuit, okay? Okay, I think for today it's enough. Yeah, the next step will be on Thursday morning. Okay, I hope that we survived this 2-hour lecture. I hope next 2 hours will be better than this. Okay, okay, so that's all for today, and see you on Thursday. Bye-bye to everybody. Arrivederci.
Bye.
Arrivederci. Bye.
Arrivederci.
Arrivederci.